Hello and welcome to another video, this time doing Math 2013 question 3. My thoughts on this question were, I like the geometry in it. I like this part, for example, when you're talking about graph transformations. I don't mind part 1. What annoys me about part 2 is it's too obvious and it's worth 4 marks in the mark scheme, but we'll get around to that in a second. And part 5, yeah, it's tricky. The last bit's always tricky, isn't it? I'm not claiming I'd get that right in the 22.5 minutes that you have to do these questions. But yeah, I did actually like, though, many parts of this question. So, okay, let's have a look at it. Without evaluating them, write down expression for a of k in terms of two integrals. So we've got to find the area here, because a of k represents the area of the shaded region for this. Now, clearly, we're going to have to integrate this bit. This bit's going to be positive, whereas this bit's going to be negative as an area. And so rather than adding the two integrals, we're going to subtract the second integral. So we take away a negative area, which obviously isn't possible, but we take away a negative area, making it positive. So we actually find the genuine area rather than the value of the integral. So, okay, let's go. I'm going to write down a of k equals, obviously between k and 0, we want to integrate x minus k, x minus 2, and take away from that, from 2 to k, x minus k, x minus 2. We know, sorry, I'm writing x plus 2. We know that this is going to be negative, so when we take away a negative, it's going to become positive, and we get the actual area. So that's part 1, and that's, I'm sure, not a problem for you. Part 2, it's so annoying when you don't know how many marks these questions are worth, because you don't know how much detail to kind of go into. Because, I mean, my first thoughts here, I'll tell you exactly what I wrote down. Both integrals are cubics, and thanks to Wallace's rule, that's just a rule where you integrate, well, differentiate. We normally talk about Wallace's rule, but because that goes to nax to the n minus 1. Obviously, when we integrate a cubic, it's going to increase power by 1 and divide by the new power. So I said, thanks to Wallace's rule, we increase power by 1 and divide by the new power, and hence each represents a quartic in k. Perhaps some terms cancel, so a of k is a polynomial of degree 4 at most. Would that have got me 4 marks? I don't know. I honestly don't know. It doesn't feel like it's worth 4 marks. So, if you actually knew how many marks it's worth, and it kind of annoys me that I don't tell you, but if you knew, to show it in much more detail, you could even, and this is what annoyed me in the mark scheme, they said you're not required to calculate explicitly, and you certainly aren't, but they then give the answer for you calculating it explicitly, as if why didn't you calculate explicitly? And obviously because you told me not to. Anyway, what you could do, I suppose, is multiply out the brackets x squared minus x times k plus 2 plus 2k. Check these signs. Just a quick thumbs up to Alfie Parkin, who spotted an absolute howler of a sign error in one of my earlier videos. Yes, the the quality of the solutions is probably pretty similar to the production quality of these videos, i.e. not great. This is going to be the same, obviously. X squared minus x times k plus 2 plus 2k, yada, yada, yada. This is really quite boring writing this out. The point is that you eventually get to square brackets where you've got x to the 4 over 4, because you're going to get an x cubed there. That's going to be minus x squared times a constant, so minus x cubed over 3 times that constant. Oh my god. And then, let me give my hand some more space. Kx squared plus kx squared, because it's 2kx. Between k and 0, and then minus something very similar next to it. Very similar, I say, well, an identical expression here. Give you a second to digest that. Hopefully you're absolutely fine with that. Now, I reckon it's really fair to say at this stage, clearly both these expressions are polynomials of order 4 in k. Try and use the correct language. and hope that they give you, at least 3 out of the 4 marks. Hence, A of k. What the order we can write down like that, kind of like the modulus. The order of A of k is less than or equal to 4. There we go. Is that good enough for them? I honestly don't know. I've never said these videos, I don't have any any idea what they'd think of my arguments, but that's what makes sense to me. I find it hard to disagree with that. And like I say, when you look in the mark scheme, they've actually gone a step further. Well, they've said you don't have to, but if you do go a step further, and then they've given the actual final result of like simplifying that, that is a time sink though, and you don't want to be doing that. And that's why I said you're not required to calculate explicitly. So it's probably almost certainly not worth doing unless you're super quick on algebra. But let's face it, we need time to think in these questions. Now part three I didn't think was very difficult at all, because you just plug the values in, don't you? F of k of 1 of t, that's what I worked out first and just wrote it down. It was 1 plus t. Then you're going to get a 1 plus t minus k and a minus 1 plus t. And all I'm doing there, let's actually bring the thing down so you can see it, is I'm just plugging obviously 1 plus t into x there. That's my f of k. Oh, why have I got an equals there? I do write down some funny things sometimes. Yeah, credit to the person who spotted my horrendous blunder from the other day. F of k of 1 plus t, and then we get 1 plus. God, that's such bad handwriting. Sorry, it's annoying me. Let me just sort that out. Okay, so yeah, you get 1 plus t minus k, and minus 1 plus t. And then f of 2 minus k, you're probably fast forwarding this bit, I don't blame you. We're going to get 1 minus t. It just takes forever to write it down, doesn't it? It's really quite frustrating. 1 minus t minus 2 minus k in brackets, because k's become 2 minus k. That's the one thing you've got to realise, but really that's kind of obvious with a notation. And then minus 1 minus t is what you're going to get there. And then if you actually simplify it, now it doesn't actually, it's not necessarily immediately obvious anyway, because you're going to get minus 1 minus t minus plus k, and you're going to get minus 1 minus t. We're going to times this by minus 1, but that only affects one of the one of the factors in this triple product we've got here. So there's only one sign we need to change, but obviously all the signs need to change in some of these brackets, because okay, that's t minus 1 and that's 1 minus t. So if I just times it by minus 1 at the moment, I'm going to get that's the same as that, but this doesn't look like this and this doesn't look like this. However, what you can actually do is times this one by minus 1 and compensate by timesing this one by minus 1. I hope you see what I'm saying there. I'm saying basically 5 times 3 times minus 2 is the same as 5 times 3 times 2. In other words, you can times that one factor by minus 1 and times that factor by minus 1, and you've done nothing at all. You've compensated for what you've done. And now you can absolutely see anyway that the answer should be minus f of 2 minus k. What am I doing? Of 1 minus t is t minus 1, which is what we want, because then it's the same as that one. 1 plus t minus k, that's the same as the middle one. And then 1 plus t, that's the same as the first one. So that's all good. It's proved. And you do want a concluding remark, like just showing that you've actually, it's really just signposting to the examiner. You've done the job. You've done the job. make your maths easy to understand. And I apologise that my handwriting doesn't really, it looks like a bit of hypocrisy there. But okay, so that's that one. Anyway, the interesting bit: how can a graph of f of k be transformed to the graph of f of 2 minus k of x? Now this ties into something I said in my last video about like reflecting in the line y. Yeah, what x equals a value. Yeah, can I just talk to you about something very much related to the point I'm going to make here? Oh, dear, oh dear, my axes. Okay, let's say I wanted to reflect this flag here in the line x equals 2. Well, obviously it's going to end up over there, yeah? But the only way we can do it, here's the rub, is that we can only do it with our traditional one-step function transformations. So like reflecting x or reflecting y or like translate, yeah? So I'm going to do it in 2 steps. I'm going to take my original image, call this A dash. But first thing I'm going to do to A is I'm going to reflect it in the y-axis, which means all the x coordinates go negative, and so that's going to go to f of minus x. So now that is over here. And now if I want to go from here to here, clearly I'm going from 0 to 4. Yeah, I'm moving this 4 to the right. I'm moving this double the distance of the mirror line now. And that's obviously what I've got to do. If I reflect it in the y-axis first, then move it double the distance of the mirror line, I'm going to get to where I want to be. I'm going to have achieved a reflection in the line x equals 2. Now, how do I shift it 4 to the right? Well, I need to replace my x. And here's the thing to remember. You've got to replace your x with x minus 4. And that, of course, equals f of 4 minus x. And what I'm trying to show you here is that we could certainly generalize this argument for x equals k. This would always be 2k, because you always need to move twice the distance because it's a mirror line, and so all points should be twice the distance away from where they started. That's how far you've got to shift it. Oh, that's how far you've got to shift it. And yeah, basically, you should definitely know this, yeah? F of x is f of 2k minus x. Sorry, not is. Let me just take that back a bit. F of x becomes, if f of x becomes f of 2k minus x, then that reflects the original in the line x equals k. That's what it does. That's a really good function transformation. And you should definitely be good at combining function transformations, particularly these little subtleties. Yeah, remember, when you want to do something to x, attack the x. X is like substituted for x minus 2 or x plus 1 or 2x or whatever the function transformation is. But you must attack the x, like i.e. operate within where x is. You know, x gets replaced with that transformation. So yeah, that's how you do reflections in the line x equals k. Now, why is this relevant to this part? Well, look at what you've just done. And look, they want you to work out y equals f subscript k of x. Well, we're going to replace then. We're going to say, okay, let x equal 1 plus t. Yeah? Because then I can work out what 1 minus t is in terms of x. Now, the easiest way to do that is times by minus 1 and add 2. So we can now see that fk of x, you see I can now just bung in an x in here, is minus f2 minus k of 2 minus x. Now I can see clearly there are like graph transformations I need to do here, because this is just a reflection. Well, this makes all the y coordinates go from positive to negative. In other words, it's a reflection in the x-axis. Well, that's easy to do. And this is just a reflection in line x equals 1, because of what I said over here. You should be aware of that result. It's a really useful result. It comes up all the time in these papers. They love in the math, they love the function stuff. A good place to find that kind of material if you want to practice it is I think a lot of the later rounds of the maths challenges have this kind of maths in it. Not always, but like there's plenty of examples. So if you want to look into like these kind of like weird abstract kind of function questions, yeah, there's a few in there. Obviously, STEP has some. You can find them in the Timu. You can find them in any any tricky area of mathematics. Really, like they'll have some good ones of these. But anyway, so we can now write it down. It's a reflection in a line x equals 1. And a reflection in the x-axis. And they're naturally, the order doesn't matter there, so I don't have to worry about saying do this first then that. It really doesn't matter when you're reflecting in like two lines which are perpendicular. Okay, so that's that done. Now deduce why a of k equals a of 2 minus k. Well, what have we got here? If you think about it, a of 2 minus k, oh, let's write it down carefully, is the area a of k after it's been reflected after the above reflections, we'll just say. And, you know, is a reflection going to actually change the area? Well, definitely not that kind of reflection, because that's a reflection in the x-axis. So that doesn't matter. So what about the other reflection line, x equals 1? Well, no, that doesn't change things either, because if you reflect this curve in this line, then that's going to be like that side over there, and that's going to be like this side over here, if you see what I mean. So you're going to end up with this bit as your big bit over there, and this bit as your little bit over there. Reflections preserve the area basically, and I believe when I looked at the mark scheme, they seem to be happy with that. You know, I do hate that kind of you know, guess what the examiner is thinking in his head kind of aspect sometimes with maths questions. It's like, let me know what you want me to show, because I can definitely see it's true. Yeah, so is the area of OK after the above reflections, hence the area is preserved. I suppose stretches don't preserve the area, do they? But reflections like that, when when the area is still bounded by the x-axis and the curve anyway, then it's fine. Okay, so part 5. Now, this is, you know, definitely, I think my chance of getting this right in 22.5 minutes is limited. I'd have to have a very good day. Okay, so explain why are constants A, B, and C such that this is the case. Yeah, I mean, this is one of those questions where it's not obvious exactly what is the best way to approach it. You, this is the best explanation I came up with in the end. I thought, well, you know, you could, because and I saw in the mark scheme what they'd done, and this is kind of very similar, but like after a shift, because it was only obvious to me after a shift, and I'll explain why in a second. What I thought was basically let k minus 1 equal u, yeah, and then I can see, well, a of u plus 1. It could be it's a quartic, yeah. We know it's a quartic. We said it was a quartic earlier up in part 2. So okay, I can write it therefore as a quartic. I can write it as, you know, any quartic as well in terms of u, because I mean it doesn't matter, you know, if a of u is a quartic, then a of u plus 1 is a quartic. So you know, you could write it as a u to the 4 plus b u cubed plus c u squared plus du plus e, yeah. But because k minus 1 is u, well, we've got once again minus u is 1 minus k, and 1 minus u is 2 minus k, yeah. And that's interesting because what we can say is a of u minus 1, which is, of course, k. Well, we already know that a of k is a of 2 minus k. In other words, a of u plus 1 is equal to a of u 1 minus u. Now, I'll tell you why that's important in a second, but I'll tell you exactly why I went about it this way. In the mark scheme, they just said straight away, I'll suppose a of k is, and they just wrote down a quartic in k minus 1. Which is absolutely fair enough. I've just kind of done it the other way round, like because I was happy to describe. I just thought that was a typical quartic. I didn't think of describing it like, this basically with descending powers of k minus 1. I should have, but I didn't. There we go. So it just goes to show, sometimes you don't find the clearest solution necessarily. It can be probably look a bit obscure to the examiner. But the point is, because that's the same as that, well, what we also know, therefore, is that, and here I'm just saying let a of u plus 1 equal that, then a of 1 minus u, which is, of course, minus u to the a times minus u to the power of 4 plus b times minus u squared minus u cubed. I'll just write it down before I make my argument. Now, because that's the case, well, firstly, let me just explain this minus u here. This is just because if we've got, u plus 1 going to u here, then we should have like 1 minus u going to minus u here, if you see what I mean. I don't know if you can see that, like, clearly we've traded our positive u there for a negative u down here, so that's going to be going into there. But also, I mean, just look at it from the k point of view, like you can see it from that. You can kind of see it from the rearrangement though. But if since these two are equal, then what that's saying is, like, yeah, you can swap a u with a minus u in here, and that's the case. But then we can conclude, but this is only true if these terms are 0. Hence, we have the answer essentially, don't we now? A of u plus 1 equals au to the 4 plus cu squared plus e. Yeah, and they told us we didn't have to find the coefficients, and I have got the answer because obviously that's a of k equals a times k minus 1 to the 4 plus c times k minus 1 squared plus e. And so I've shown we can always write it like that. It's because of this, like a symmetry, basically. That's what that is, a little bit of symmetry. Okay, definitely the last bit though, that's hard, isn't it? Let's be honest, that's hard. They point out in the mark scheme there's other ways of arguing it with symmetry, and I was really intrigued to hear how he described it. It's like, yeah, that is, I wouldn't have thought of explaining it in that way. And, I suppose it is kind of nice that the question, especially when you read the mark scheme there, where it's like, well, we will absolutely accept a really clear geometric explanation why that's the case in terms of even functions and stuff like that, even odd functions. It's, the way it describes, I'd never thought of like what I was doing with the reflection in the line here and then another reflection as a rotation around a point. It's like, oh, that's intrigued me. It's definitely worth looking into function transformations. They're really helpful in these questions. Okay, hope you found it useful. All the best, and yeah, keep up the hard work, and yeah, good luck in the math. You can do it.